Well, folks, we've reached that second magical time in the evening. We've reached the time that our headliner's going to come out. He's a fantastic, funny man, a great improviser, one of the smartest, kindest, nicest people I know, a great friend of mine. Please put your hands together, sound like 2 million people, for Mr. Jim Gaffney.
What up, peer review? Wow, you are a beautiful audience. Yeah, give it up for everybody who's been on stage tonight. Well, I would like to thank you for sticking around. I am going to tell you tonight why I believe quantum mechanics is the most existentially comforting of all the physical sciences. Now, I will say, I want to preface this, I am not quite the subject matter expert like the people you have seen come before me. But the second time I took undergraduate quantum, I got an A. Proving that you can bullshit your way through more than the humanities. Now, quantum mechanics fundamentally changed my life. It changed the way I think, it changed my thought process. It completely altered my perception of the world. Because quantum mechanics is completely unlike the other physical sciences. Quantum mechanics is kind of a science that you have to take on faith, which is a weird concept. But if you take something like classical mechanics, it's very black and white, true and false. If you give me a set of information, I can tell you everything about this particle in its entire history or past or future. It's deterministic. Quantum mechanics is none of those things. Quantum mechanics is entirely about shades of gray and indeterminants and uncertainty. They even have a principle named after it, the uncertainty principle, which is the biggest cover your ass move in physics. Now, it's different in that respect, but it is still a hard physical science that is grounded on a foundation of rigorous, coherent mathematics. The only difference is it's a rigorous, coherent, probabilistic mathematical foundation. And it's that probability part that opens the door for arcane philosophical interpretations about its consequences, or predictions of fantastical physical phenomena, things like quantum computing, or the existence of alternate parallel universes, or quantum tunneling, where a particle passes directly through a wall. Now, I know what you're thinking. Hold up on that last part. I didn't phase through a wall, and I spent 2 hours banging my head against it after I listened to Fox News. Well, that is because you are a macroscopic object. And now some of us are more macroscopic than others. But in the eyes of quantum mechanics, we're all the same. Quantum mechanics arises out of the wave-particle duality of matter. All matter exhibits properties of particles and properties of waves. And when you're a macroscopic object, we are like particles. But as you get very small, as your mass decreases to something like an electron or a neutrino, that is when the wave properties begin to take over. And that is the realm where quantum mechanics rules. Now, all right, thank you, one person. Now, the first person to put any math to this, any legitimate math, was Dr. Erwin Schrödinger, noted mathematician, physicist, and cat lover. And he developed the Schrödinger wave equation, which is a very complicated piece of mathematics. And if you looked at it, it would be just as home in a Greek text as it would be in your physics textbook. Loosely translated, I believe it means, your cat might be dead. Now, it's an incredibly complicated piece of math. And to conceptually wrap your mind around what it means physically, physicists look at it through the lens of statistics. And this is where we introduce those elements of chance and probability and uncertainty. And these are all things that physicists just hate. because it breaks with everything they thought previously. And if you've ever heard that Einstein quote, "God does not play dice with the universe," this is exactly what he's talking about. And you can see in his argument to fellow scientists, he was invoking the Almighty, which tells you where his head was at the time. Now, there's another universe where I didn't forget this part. There was the first major hurdle that quantum mechanics had to overcome in its bid for acceptance was not just a problem for physicists, but this was also a problem for men everywhere, insecure men everywhere, and this was the measurement problem. Now, to understand the measurement problem, we are going to use the Schrodinger's cat thought experiment. So if you could all take a second and go into your mind laboratories, I need you to pick up a few supplies. An opaque box, a device that has a 50-50 chance of releasing poison at any given moment in time, and a cat. Why a cat? Because a cat has a 50-50 chance of giving a crap about you at any moment in time. Now, you take the cat, you take the poison device, you stick them in a box, you close the lid. Now, I open the lid to my box, and I see a dead cat. Sidebar, my cat is always dead. Something my therapist and I are working through. I close that lid, I open it again, the cat is still dead. I ask quantum mechanics, hey, what's the state of my cat right now? Quantum mechanics is going to tell me it's dead. No matter how many times I ask it, it will tell me that I have a dead cat. But if I flip the question and I say, hey, quantum mechanics, what was the state of that cat right before I lifted the lid and looked at it? I don't know. It was half dead, half alive. It can't answer the question. And yet, after the measurement, it can give me the answer that I observed every single time I ask it. That is the measurement problem. And that's indeterminates. And now, this caused a schism in the physics community. And all the scientists split up into three major camps. And the first camp were the agnostics. And these people were lazy. This is the camp I would have been a part of. And what they said is, you can't know the value of something before you measure it. That's impossible. So why are we even bothering to ask the question? Ambivalence is always rewarded in science, and shockingly, these people were proven wrong. The second camp were the realists. And these people said, in order to be a legitimate theory, quantum mechanics must be able to answer this question. And if it cannot, then that means that our understanding of quantum mechanics is incomplete. In other words, we have a view of what a scientific theory is, so quantum mechanics has to conform to it, otherwise it's wrong. These are like Fox News people. And this was the camp Einstein was in. And maybe it's the schadenfreude of being a failed astrophysicist, but I love those times when Einstein was wrong. And this was one of them, because it was the third camp, the orthodox camp, that eventually came to be accepted as the right group to be in. And what they said is, the act of measurement is unique and special. So, before you open the lid and measure your cat, your wave function has two peaks, 50% at dead and 50% at alive. And then you open the box, you look at your cat, oh, dead cat. Then the wave function collapses to be a single peak at 100% bona fide dead cat. Measurement is special. Measurement causes that wave function to collapse to the observed value. And this was all well and good for a couple decades, until the mid-50s. A guy named Hugh Everett came along. And he didn't like the idea that measurement was special. He did not think that the wave function should have to collapse. He did not think that measurement should be this mystical power that we all have that interacts with the fundamental forces of the universe. So he set out to develop a formulation of quantum mechanics that did not include a collapsing wave function. And he succeeded. He used pure wave mechanics, basically pure math, and he developed what became known as the many worlds interpretation of quantum mechanics. This is the scientific and mathematical justification for the existence of parallel universes. That's not science fiction. I love that. This wasn't something a comic book writer came up with to get Superman out of a jam. This is actual science. And so how things work is like there's no more collapsing wave function. So before I open my box, I have my 2 peaks at alive and dead for my cat. And after I open my box, I still have my 2 peaks at alive and dead. So why do I always know, or why do I always get the answer from quantum mechanics that my cat is dead after that? Well, according to relative state theory, or Everett theory, or many worlds theory, it has many names theory. It is because the supposition of all of the wave functions in my universe makes it so that I can only perceive dead cat. The implication of that being, there is an entire other universe where in that box is a live cat. And lifting the lid on that box is a much more optimistic and well-adjusted Jim. And that is what makes me feel better. Because no matter how bad my life is, no matter how bad things are going, I know that there are multitudes of universes with Jims who have it way worse off than me. And it gives me hope, because I know that there is an infinite number of universes full of Jims who have overcome obstacles and achieved and done great things. Somewhere there's a universe with a Jim who solved world hunger. Somewhere there's a universe with a Jim that doesn't pee in the sink. Somewhere there's a universe with a Jim that's a choreographer for Shakira. And it also gives me explanations for things that I just can't understand. Maybe, just maybe, Fox News isn't an evil propaganda corporation. Maybe they're just reporting real news from a universe in which we don't exist. So when my lizard brain acts up and it's feeling the existential dread of living a pointless life in a random and chaotic universe, where am I going to turn for comfort? To a rigorous mathematical formulation, or to myths and stories passed down by humans about a supernatural socialist? I'm sorry, Jesus. I choose quantum mechanics. Thank you very much.
Keep it going loud for Jim Gaffney.